Tom Evans, thanks so much for joining me today.
You bet.
So you're a distinguished research and development staff at Oak Ridge National Laboratory. And before we get into your work that you do there, I want to learn a little bit about you. So are you from Tennessee originally, or where did you grow up?
No, I grew up in Pennsylvania. I was actually born right outside of Philadelphia in New Jersey, and was a part of youth in Philadelphia, and then most of my childhood in Reading, Pennsylvania, until college.
Is Reading like a farm area?
No, actually, it's a lot like Knoxville in terms of size and general geographic structure. I mean, it's just farther north in the Appalachians, really. But yeah, it's kind of a old industrial Pennsylvania city. So about 40 miles northwest of Philadelphia.
And is that where you did university then?
No, I actually went to school in Philadelphia. So I went to undergrad in Philadelphia at Haverford College. Then afterward went to Georgia Tech for graduate school. So,
awesome.
So yeah, from Philadelphia to Atlanta. I still have a lot of family in Pennsylvania, but I actually haven't lived there since about the age of 20, 21, I guess, technically.
Yeah, Tennessee's got its hold on you?
Well, so far so good, I guess you could say. I've been here for a little over 12 years now. So
that's great.
We like it.
And so did you go undergraduate in Pennsylvania directly to a graduate in Georgia Tech and then directly to Oak Ridge?
No, so I went from Pennsylvania, went from college, went to graduate school at Georgia Tech, and I was in Atlanta for 4.5 years. And then I actually went to Los Alamos, New Mexico. So I was at Los Alamos for 10 years before coming to Oak Ridge. So yeah, growing up in Pennsylvania, about the last place on earth I think I expected to be when I was a teenager was New Mexico, and then Eastern Tennessee. But that's how things work out.
Yeah, and here you are, and it's going well. So
yep,
you never look back.
That's right.
So what did you study in college?
So I was a double physics astronomy double major as an undergrad, and then when I was looking around, for graduate school, I actually originally thought I was just going to go off and kind of get a master's degree in mechanical engineering, and that's the school I applied to at Georgia Tech, was actually mechanical engineering, and went and at Georgia Tech, the nuclear engineering program is actually inside the School of Mechanical Engineering, and so the first semester there, technically quarter, because it was on the quarter system back then, I kind of because I had a background more in physics than engineering, I kind of got involved with an advisor who was doing work in radiation detection, which was in the nuclear engineering side. So that's actually how I ended up in nuclear. So that was never really my plan, to say.
Yeah.
And even then, I got a PhD in nuclear engineering, but I never really, in a sense, was considered myself actually kind of a nuclear engineer, at least a nuclear engineer from the, reactor design standpoint. I really did almost all my graduate work in kind of applied physics and math and radiation detection. So building detectors and then writing simulation codes to simulate the detector responses is what my thesis is in. And then from there, I'm kind of being long-winded here. Should I keep going?
No, go ahead. Yeah.
And so there, went off to Los Alamos and spent 10 years working in kind of computational radiation hydrodynamics, because that's the mission at Los Alamos, obviously, is very closely associated with defense applications. So
radiation hydrodynamics, is that like radiation traveling through the air?
It kind of is. You could think of it more like the processes that occur like in stars. So for example,
wow.
Basically it's the tight coupling between what we would think of as like thermal radiation. So, and then fluid flow. So that's, for example, this is the process that powers stars. And, I'll let you extrapolate why places like Los Alamos would be interested in something like that.
Yeah.
But, and I had never done that as a graduate student either. So yeah, I've kind of reinvented myself at least 3 or 4 separate times, going from place to place. And so, worked at Los Alamos for about 10, for almost exactly 10 years, and came to Oak Ridge. And since I've been at Oak Ridge, it's been much more in the, more what I would call bread and butter nuclear engineering side.
More of like design side, you mean?
I'm still doing a lot of the same computational work. I did a lot of the techniques and algorithms and equations that we try to solve. If they're not the same, they're very similar. It's just for a very different application space. So now I predominantly lead a team that works on modeling and simulation computer codes that are used to help design nuclear reactors or characterize them. Yeah.
Yeah. In your undergraduate or graduate, then, was the focus of the degree really heavy on programming and computational models?
Yeah. As an undergrad, I did quite a bit of work in both math and computer science, but I was in more of like what we might call a classic physics curriculum. So it was very much stressed on kind of very much fundamental theoretical physics skills and lab skills more than it was computational skills. This was also, seems like a long time ago, but probably wasn't, depending upon who you talk to. But I was in an undergrad from '88 to '92, and that was still kind of in the by today's standards, kind of on the early side of doing high resolution modeling and simulation. So it really was, the focus was still very much on theory. We did a lot of work. We did a lot of early work on computer mod sim there, but as part of our curriculum. But it was nothing like what people are doing today.
Yeah, which people like you are doing today.
I guess, yeah, that's right.
That's what you're doing. Right. Yeah, so you've developed with the field.
Yeah, pretty much. Yeah, I was very lucky in the sense that I got to Los Alamos in early 1997, and at that time, a big program had just started, which was the Advanced Strategic Computing Initiative, or ASCII, which was a big project at what are now the NNSA labs, which are Los Alamos, Sandia, and Livermore, basically to supplement or to replace what had been nuclear testing, which had undergone a basic voluntary, not an official moratorium in 1991. So they were no longer doing active tests. So they had a bunch of legacy mod sim codes they used to use to supplement their testing, and it was an iterative process where you would use these simulation codes to kind of perturb and help refine designs. You would go test it. You would then iterate, and you would iterate on that process. Once they stopped testing, there was a strong need to make the simulation part take the place of the testing part. So it was a matter of putting a lot more physics, a lot more fidelity, going from 1D to 2D to 3D simulations, all together, and doing much more extensive, detailed coupled simulations. And along with that was this big initiative. What ASCII brought into that was to both beef up the modeling simulation capabilities for doing this, but also that was tightly coupled with bringing in kind of the first really big, highly parallel supercomputers that are now common for example, at Oak Ridge, like in the Leadership Computing Facility at Oak Ridge and at Argonne's Leadership Computing Facility. But that was kind of really kickstarted by in the ASCII program. So I kind of was lucky to get there on the close to the ground floor, as it were. So yeah, I was able to kind of grow with that community.
Yeah. And have you noticed, I guess, in your train of thought as you do grow with it, as you go from 1D to 2D to 3D modeling, do you ever look back and think like, wow, how did we, make decisions based on this old method of modeling?
Well, what you actually realize is that two things, and if you think about them too much, in some ways they're almost they're highly interesting, but they are also a little bit depressing in that one, that everything we're doing now was kind of sometimes I think was thought of by somebody before. They just didn't have the means to do it.
Right.
That's the first one. And the second thing is that those guys were really, really smart back then, and they came up with lots of really clever ways to approximate effects that we're actually now, in a sense, it's a couple steps backwards to go forwards. We're actually able to kind of do almost more brute force approaches that were just inconceivable for because we have computing power. Now, they bring their own sets of challenges with them, but nonetheless, guys back then had to be very, very clever to feed enough information into something that was really a low resolution model to kind of simulate reality. Right now, since we're able to, we have a lot more computing power at our disposal, we can actually do much more direct simulation of the real physical models. Of course, again, that brings in its own spectrum of challenges that are different, but they were really, when you look back at some of the stuff that was done, they were very, very clever.
Yeah. Yeah. So let's talk about some of the challenges. What are some of the challenges that you guys see with the simulation models?
Okay, so a lot of the big things right now is that I would say, science, or at least let's say physics, I don't want to be quite so broad as to say science, kind of had two traditional communities, right? You had theoreticians and you had experimentalists. And now we kind of think of people, and computation kind of grew out of the theorist side, and now it's really kind of its own field in and of itself. And this is something that's, I would say, loosely developed over the last 20 to 30 years, where computational physics is almost could be classified its own field of its own endeavor that's kind of separate and kind of sits between, but with lots of gray area between kind of pure theory and experimental simulation or experimental work. When you think about, computation, for the first 10, 15, 20 years of that part, a lot of people were focused on what I would call kind of single physics simulation. So the idea being you have a model that's going to look at kind of one thing. So for example, I might look at the neutron behavior in a reactor core, or I might look at the fluid flow, and it doesn't have to be necessarily in a reactor. It could be in any kind of modeling and simulation. I might look at the airflow over a wing for if I'm doing aeronautics or something like that. But I'm not coupling that together. In reality, none of this happens in a vacuum, right? When you have airflow over a wing, you also have heat transfer across the wing. When you look at it in a reactor, the neutron behavior is coupled to the fluid flow behavior. And we used to do those things very loosely for a long time. And so a lot of people had long careers where they just looked at one part of, one spectrum of physics. So they looked at a couple different types of models or model equations and spent all their energy improving those or trying to come up with new mechanisms for solving those. Now what we've really expanded into is trying to do what we call coupled physics simulation. So it's, we kind of feel like, well, we've kind of hit the neutron problem by itself. And we've already hit not that there's not more work to be done individually in those, but there's much less impact to be made just by improving models that do neutron transport or improving models and algorithms that just do fluid flow. The idea is to do actually fully coupled simulations. And so now it brings in a lot of extra complications in terms of the fact that when you have neutrons, for example, interacting, heating up nuclear fuel that creates temperature that feeds back into the fluids that are flowing by it to cool it, and then the density changes. There's this feedback loop, and so you have to capture all of those effects, and then you also have to understand lots of different branches of applied math and physics as well. So that's where the challenge is that it's harder to just kind of, especially at a national lab where we're trying to do big science as opposed to one person sitting there trying to make small incremental improvements to one thing. At national labs, our objective is really to solve big problems, and so it means that you have to, there's a much bigger spectrum of things you have to get comfortable and familiar with.
Yeah, absolutely. And what are some of the big projects that you're working on right now?
So myself and my team are highly focused right now on a DOE project called the Exascale Computing Project, and what this is it's actually the largest computing project inside of DOE. It's maybe in fact the largest project ongoing right now in the open science part of DOE. I don't know that for absolute fact, but it's
large in this sense. Is it large in the sense of the number of people working on it, the
both.
funding
So
going
it's
into
about
it?
It's a 7-year, $2 billion project, roughly $2 billion project that basically involves every lab in the DOE system and a significant number of universities. I'm not 100% sure of the total number of institutional partners, but you have something on the order of, 14 to, what do we have, 17 labs? 17 national laboratories, and many universities all working on trying to develop applications for the next generation of supercomputers. So in 2023 at Oak Ridge, for example, Oak Ridge is going to launch the Frontier computer that's going to be, the target is to be capable of performing 1.4 exaflops of calculation.
What's an exaflop?
Exaflop is big. It's 1,000 times bigger than a petaflop. Does that help?
Only a dash.
Right. So basically, X is 10 to the 12th. So am I right on that? I think so. No, 10 to the 9th, 10 to the 12th, 10 to the 15th. Sorry. These, okay. After a while, these things all become relative, right? So, so that's the number of floating point operations per second. So when we think of an algorithm, when we think of something that we're going to have a computer do, we can think of like the number of mathematical operations it can do per second, because ultimately you're solving some mathematical expression, right? The more mathematical operations it can do per second, ostensibly the more computational power it has to solve a problem. Right. So basically this is a, right now we have the Summit supercomputer on the floor, which is the fastest or most powerful computer currently in the world as measured by the top 500, the HPC top 500 list. And that's currently running at around 200 petaflops. So this next machine is going to be roughly a factor of 7 times more powerful. And Summit itself is a factor of 7 times more powerful than Titan, which is the machine that we just retired here. So the bottom line is DOE is constantly planning to put more and more powerful computers on the floor. And what they want to be able to do is have the kind of portfolio of physics and chemistry and science applications that can use that computer ready to go by the time the machine lands. Because otherwise the machine is here, and if you don't have anything you can run on it, then it's not much, then it's a, $150 million white elephant, right? So the idea is that you want to be able to do significant science and engineering simulations with these machines as soon as they're here. So what we're trying to do is we have 24 specific applications and along with a host of supporting technologies.
Within nuclear? Within
Exascale.
Okay.
We are running those 24 applications span a wide range. So there's molecular dynamics, there's wind power simulations, there's carbon capture, combustion and engine simulation, cosmology, stellar astrophysics. There's a whole wide range, climate and earth science. So there's a earthquake simulation. There's a whole range of applications. We are running the application that has to do with nuclear reactor simulation. So specifically, the way each of these projects are organized is that each project kind of is in one domain science area. So we're running the nuclear domain science area, and then it's built around a challenge problem because we're trying to measure performance. So the challenge problem we're currently attacking in this is the startup modeling of small modular reactors. Now, it's not the tools, the computational tools we're building to do that will be able to be used on Summit, that are currently being tested on Summit and that will ultimately be used on Frontier, can do more problems than that. But the idea is that you target a specific problem so that you can measure as you go from machine to machine, the improvement in performance, improvement of physics fidelity, and things like that. So we picked a representative problem, which is important in the nuclear space, which is obviously there's a lot of excitement about small modular reactors. And so the idea is that we picked that as an up and coming nuclear technology that's a good problem to look at.
So is it easier to model an up and coming technology that doesn't necessarily have a set design right now, or has that been a challenge?
So this kind of gets back a little bit to what we started in talking about, in that the short answer is it's a little bit complicated. So it depends on what is being looked at. So on the one hand, For a long time in nuclear, up to the current day, we use low order models that can be run on, you could run it on your laptop or a desktop, because they run, basically fuel vendors and utilities run thousands of these calculations all the time. To optimize their fuel cycles, to look at fuel performance, to do operating conditions and everything like that. And then what they do is they correlate these calculations, and the data that goes into these calculations are tightly correlated with the vast reams of experimental and operational data we have on hand. So we've been running nuclear power reactors in this country in the world, but in this country for, 60 years. And we've had a slew of experiments that supported the development of those reactors as well. So reactors that are up and currently running, we have a large spectrum of data that we can look at. And then what we can do is we can, say, tune these low order models so that they fit within the data points. So, we may not know, between this point and this point exactly what's going to happen, but we can run at this point, run in this point, and see that we fit, right? And then we can kind of figure out what's going on between them. What happens when you're looking at a new design where you don't have that experimental history, all right, or operational history, you're kind of operating a little bit in the dark. So you have to, be confident that you have the right physics models involved and that you actually, can calculate things ab initio from first principles, because you don't have bounds that you can bound your calculation with from experimental or operational data. Now, in terms of the difficulty, that depends on what the design is. So, for example, doing a full high fidelity model of an existing, say, PWR 900 design that you might see at TVA or any number of plants across the country is actually there are aspects of it that can be very difficult to simulate and model. Like, for example, departure from nucleate boiling, try to detect where boiling is potentially happening in small regions, because the reactor is so big, right? It's a very large system, which requires a tremendous amount of computational resource just to be able to run. A lot of the new designs, like SMRs, obviously, you can probably guess from the name, being small, is about, physically is only about the quarter of the size, or even a little less than a quarter of the size of a current PWR in operating today. So from that standpoint, it's simpler because you can actually, you have less constraints when it comes to, for example, fitting the whole problem into memory or your available memory. The number of effectively the number of equations you have to solve is smaller. The number of unknowns are smaller. But then again, because the system is smaller, it has other features that make it potentially more difficult to model. So one of those examples is that proposed SMR designs are all built on natural circulation. So what that means is that there's no pump that drives the coolant through the core, right? So that as the coolant goes through the core, it picks up energy from the fuel. It goes through the primary heat exchanger and then, recovers that as it drops down in the coolant loop. That's all done through driven natural circulation, simply from the power of the core. That's a strong modeling challenge because you have to calculate and accurately predict those fluid flow effects and the interaction between the fuel and the flow to get that right. Whereas in an existing PWR, even though it's very big, the reality is those are driven by pumps, which means that you always have a fixed inlet condition for example, for the pressure of the coolant coming through the core. So even if you don't get things exactly right outside of the coolant loop, you always can kind of fix it up as it's incoming. So in terms of capturing the behavior of the core, you can use a much lower resolution model to capture that, even though it's a much bigger problem in a sense. So it's kind of can be there's kind of two aspects. On the one hand, you do have a ream of experimental data, so you can rely on your knowledge of experimental data points to bound your solutions, and you can get away with using lower order approximations to first principle physics. In a new design, depending upon the design, there could be features that make it much harder to model and simulate, or that you have to use much higher resolution. And you don't necessarily know what those things are coming out of the gate because you don't have this wide space of experimental or operational data to compare against.
Yeah. And also I would think that because you were saying that you basically use data from operating plants to extrapolate some different scenarios for pressurized water reactors, which you already have. But for the small modular reactors, like you can model what a design would look like, but you don't actually have a physical design ever or any data ever.
Right now, there's none operating. I think this is a little bit outside my, my direct realm of knowledge, but I think the idea is to stand. Originally, there was a target to stand a prototype up in something in the 2025 time frame. And I think, I'm not sure if they're still on that target or not, but, all the new reactor designs they're potentially looking at, whether it's SMRs or micro reactors, have some of these same effects, is that, we don't have, obviously we don't have operational data because there are none operating. And then the other part of this is that there was a whole enterprise that involved labs and universities where, we had a whole fleet of research reactors and subcritical experiments around the United States, in the 50s and 60s that helped feed even beyond just the straight operational data, that helped feed the growth of the original, first generation and second generation growth of our nuclear industry. Those facilities don't really exist anymore, and the ones that exist, certainly not in the same numbers.
Right.
And so you're forced to fill in those gaps with high resolution modeling and simulation and knowledge, as opposed to just straight experiments. And there's multiple reasons for that, but a lot of it has to do with simple fact that experiments of any type, especially experiments involving nuclear fuel, are just, much more expensive to set up and run than they were 50, 60 years ago.
Right.
So we have to kind of go about this in a different way.
And it's like back to the way basic question of why do we need to model and why do we need simulations? What are you modeling and simulating, especially for, the reactors that we already have that are up and running?
Yeah. So that's, so basically what you're, this gets to be, this could be kind of, a complicated question, but it's really the idea is to optimize the design process. So for any engineering problem, you're looking at, there's constraints on operating. You don't have unlimited time, and you don't have unlimited budget, and you don't have unlimited material resources to build these things. And it doesn't matter if it's an airplane, a nuclear reactor, or what have you. And so what you're constantly trying to do is you need to refine designs. It's not like you're going to build a reactor, try it, and see like, oh, we're exceeding tolerances on the fuel in this part, all right? Because and obviously with anything nuclear, there's going to be a very high safety component as well. There should be. So there's strong, and then coupled into that and overlapping all of it is there's a strong regulatory component as well. So one aspect is that before any reactor can become licensed and operational, the NRC has to certify its design, right? So the NRC is very interested in being able to have an independent set of tools to run that's distinct from what was used by the manufacturer or the fuel vendor to certify their design calculations to make sure that everything is in line with what they say it is before something can be built and operated. So that's from a regulatory safety standpoint, that's one part of it.
So that's you guys, right? You're the verification, essentially.
Essentially, we work with the NRC quite a bit to do that. So yeah, that's definitely one big part of what we do. And the other part is simply to just again, to just extend the kind of knowledge base of how everything works. And part of this is that in engineering, I think of there are two kind of realms of computation, and there's kind of what I call discovery science, and then there's engineering. And so, for example, a good example of discovery science is for people who are trying to just extend our knowledge of fundamental nature. So for a simple example, or a simplistic example, is people who do modeling of astrophysics for stellar supernova. Well, we observe supernova. We know they're out there. We really don't understand all the physics that goes on to create a supernova. No one's ever sat next to one and watched it. We don't have direct measurements of it. So what they tend to do is what they figure out is like, okay, let's try, we think a supernova works like this. We think two stars, collide and collapse in on each other in this way, and it, gravity works this way and heat flow works this way, and then they'll develop models for that, and then they'll do a full simulation, and they'll try to correlate that simulation back to something we observe here on Earth, or at least here in near Earth orbit. And if they can do that, they've kind of learned something fundamental about nature. They've said, okay, this is actually how this is happening, and this is the models, or this is the mechanisms by which this happens. So you can think of that as like discovery science. In engineering science, what we're more interested in is optimizing and understanding the design process of something. And in that case, you're much less concerned with the fundamental physics involved, and that not that we know everything that's going on inside every engineered system we have, but generally the physical models are more well understood because it's something we can build and we can look at and we can touch and everything else. But what we want to be able to do is run higher fidelity, more resolution, more spatial resolution, more energy resolution, more angular resolution, whatever region of phase space you're interested in. We want to be able to run that more accurately and faster. So we can do more design calculations. We can put the thing under more constraints. So for example, what happens if there's a fluid coolant leak here? What would happen? What happens if there's a clad break or a clad, so we can run many more types of scenarios to optimize the design parameters more efficiently and more accurately. That's more what I consider engineering science. So on the one side, you're dealing with models that you may not understand so well, but you're not as concerned with how accurately you solve them. You're trying to meet kind of what I would call, rough or order of magnitude approximations. On the engineering side, you tend to have a lot more comfort that you understand the physical mechanisms involved. Are you including enough of those physical mechanisms in your model, and can you solve them quickly and accurately enough to actually model and look at something that's of interest? Okay, and then there's obviously a lot of overlap and gray area between there. Obviously, people who are doing, cosmology and astrophysics do care about the accuracy of how well they're solving something. And we don't know everything that goes on inside of every, part of a nuclear reactor. An example where modeling and simulation has, helped in the nuclear side, even in our existing PWRs, is for example, the issue of CRUD, which is my favorite acronym in the world.
What?
CRUD, which is the Chalk River Unidentified Deposits. So on existing reactors, what they've found is that when they've taken fuel out and looked at it, you get this chemical buildup of stuff that forms outside the clad. Okay, and so what happens is that affects the fuel performance. And so, the longer you can keep an operator operating in its fuel cycle, the more efficient it is, the more economical it is. And our existing reactors were built with highly conservative margins, right? So the fuel cycles used to be something 9 to 12 months, and now they're 16 to 18 months. And as the more we learn about them, the more we realize we can reduce those margins and still safely operate the reactors for longer, which means they stay up longer. When you switch fuels, it's, first of all, you don't get the full efficiency of burning the fuel. Second of all, it's a very expensive process. You have to stand down the reactor. You have to have all the radiation safety people in there. You have to move the fuel. And also the fuel is obviously hotter because so you have to store this hot fuel on site and things of that nature. If you can burn the fuel more efficiently, if you can burn it longer, it's just a win all the way around. So one of the things you want to do is optimize how long you can run a fuel cycle for. So things that affect the fuel cycle performance are things that were outside the design specifications of the reactor. So for example, these aren't necessarily safety issues, but for something like when you have these CRUD deposits that develop over time on the outside of the fuel pins, it affects how long you can run the core. And so if they can understand how those things form, you can actually go about addressing it. So one of the things we tried to do in the Castle project, which we haven't talked about, but Castle was the original energy innovation hub that was a big DOE project back in 2012. That was also led out of Oak Ridge that I was a part of. And one of the problems was try to figure out if we could do coupled chemistry, neutronics, and flow calculations, because this is a chemical process by which these things, by which this stuff forms on the outside of the fuel rods, can we actually predict the formation of crud that these low order models that are used to both predict an operating fuel cycle and were used for the design can't do, because they just don't have the necessary physics and models to do that. So there's all sorts of things that always come up in any system that you're trying to figure out and, both understand from a scientific standpoint and then try to engineer solutions for. And that's why we're constantly working on these processes.
Yeah, it's a lot to all put together. And there is, I think, a big exploratory portion of it and then engineering portion of it that needs to go together so that you can, test different scenarios that maybe are a little bit more out of the box, but still make sense from an engineering perspective. And you had mentioned that there's a lot of attention to safety and that there's a lot of regulations that obviously go into the operation of a nuclear plant. And so since you're, the guy behind the modeling and the simulation, do you ever take hold of that sort of exploratory route and say, okay, if there wasn't these safety regulations or if there wasn't these regulatory restrictions, this is what the plant can do, and sort of play around with different parameters?
We do. We sometimes, I would say it's more like, let me answer your question a slightly different way. So one of the things we have to be very cognizant of is when we're trying to develop really high performance or high fidelity simulation tools that people can use to do validation or what have you, we have to be very careful to say like, oh, well, for example, utility couldn't come out and say, well, we have this amazing set of codes that can run on Summit that can, model everything down to the individual fuel pin level and give us the very precise, accurate data on, the fuel performance, on the chemistry and everything else. Because the NRC turns around and says, well, then you can't certify the design until you get time on Summit. Well, no one has Summit sitting in their facility, right? There's one in the country, in the world. So one of the things we have to be very careful about is that we balance what we're doing inside of this kind of regulatory framework so that the designs can be certified and they can be certified in such a way that they don't absolutely depend on us. So that's already kind of baked into the whole thing that you're asking. In some sense, we are the outside the box part. And what we're trying to really do is take the place of experiments. So, what we try to do is say, like, we can run virtual experiments for you, right? So we can get on the Summit and we can run various operational reactor scenarios and create very high fidelity data that almost takes the place of some experiment somewhere. And then they can take the results of this data that, and they can use this to benchmark their own workflows and processes by which they're doing the design. And they can use this, in other words, to find those points I was talking about before to interpolate between in the absence of real experimental data. So that's kind of how a lot of these things are used at the high performance computing end, simply because it can't be part of the direct design process right now because most places just don't have that kind of computing power. We're sitting out, 10, 20 years beyond, maybe that's a little exaggeration. We're sitting out a certain number of years beyond what the existing kind of industry or institutional level computing resource that most places can operate in. So that, a natural follow-on might be, so what does this matter if not everybody has access to these high performance computing resources? Why do you do it in some sense? And there's actually a more interesting answer to that question. And the answer is, today's high performance computer is tomorrow's desktop and it's, next week's laptop, right? So if you think about, your cell phone back in 1979, 1981, the Cray T3D, which was used at Los Alamos to do all their kind of design weapon simulations, was about, 1/3 the size of what you can do on your cell phone, right? And that was the largest computer in the world by orders of magnitude at the time. So, your cell phone has vastly more computing power than, what we used to think of as the absolute cutting edge. These were hand-built, unique machines. And so by continually pushing our models and algorithms forward, what may be only capable on Summit or Frontier today, in a couple years' time, will be available and be usable on what is achievable at an institutional computing level. So that's why we sit at this kind of cutting edge, is because by being at the cutting edge means that tomorrow, the next day, it's going to be available everywhere.
Yeah. It's extremely fast paced, which is good. I think that's a little bit of what the nuclear industry needs.
Yeah. We're trying. Yeah, we have to keep up. That's for sure.
Yeah. And in your modeling, have you ever modeled something and sort of realized, okay, maybe our regulations are off? Maybe we don't need to regulate it as stringently as we are?
That's
a hard question.
Yeah, it's not. Yeah. You're getting a little bit out of my comfort space, because I never know 100% what I'm allowed to say on that kind of thing. It is true that we have captured startup conditions, actual measured startup conditions, considerably more accurately than other calculations that were still within tolerance. Mm-hmm. So and that still were in spec, but the short answer, I guess, that I'm comfortable giving is, in some cases we can do a much better job of capturing, of simulating certain effects and certain phenomenon. But in terms of how that feeds back into the regulatory framework, I'm going to take the coward's way out and say that's a little beyond my pay grade.
I'll let you get away with it this time.
Okay, good.
But I think I hear an answer in there. And then when you do your simulations for the SMR, is it, and correct me if this is already in line with what you do, but why can't we just say, okay, I have this design on paper, I'm going to computerize it and do some models on it so that I can run it virtually. So it's like I have an SMR and it's running and this is what it looks like as it runs. Why can't you just submit that to the regulator and then, get a license to build based on that without making, say, like a physical test?
Okay. First? So, that's kind of so the first part is that as a national lab, we're kind of, we're not directly, we ourselves aren't building the reactor. Right. So for example, if company A is putting a licensing package to say, we've got a design for a SMR, we're not necessarily part of that design process because kind of there's a conflict of interest there because we're a national laboratory. We can't be seen as working directly. We're there to help industry for sure, but we can't be seen as working directly for them in a sense. And then we've hoped we're in contact with several different people that are working on advanced reactor designs, and we're trying to run calculations that are of interest to them on models that are of interest to them. But there's a lot of, unfortunately, it's the nature of the beast that there is a lot of legal hurdles there. So for example, we can't get the exact design of the people we're working with for their SMR right now, because it's proprietary. They're not, they won't release it to anybody. It's got, copyright control and proprietary controls on it. And since we're an open science lab and everything we do needs to be made public in that sense, if we were to see running that exact model, people could look at it and say, oh, I know what their spacer grid design is. Like ostensibly a competitor could look at it and see that, right? So there are issues involved there. So there are proprietary and copyright control issues, and intellectual property issues. That's one issue. That's one part of it. The other part of it is that even at this, we're constantly, like, as I said, trying to kind of push, the bounds as far as we can of what can be done. And generally what we're doing is it's the feedback loop in some sense is more that they see what we're doing and they're trying to incorporate parts of what we're doing, having demonstrated that it works, into their workflows as opposed to using in some cases directly what we have. They do that as well. But the reality is they have to show a certain amount of independence. And this gets back to something I'd said before, is that, they can't go to the NRC and say, well, we ran these calculations on, Summit, because they can't be guaranteed they're going to have time on Summit next time. To get time on Summit is a competitive process in and of itself. It's not like, you just walk in and, sit at a keyboard and just start typing like it's your local library, right? You actually have to, submit a proposal, and get time. There's only, there's lots of people around the world that want to use that resource, and it's a competitive process. So obviously they can't come up with a business model that's dependent on a competitive process to get time on a computer. They have to have something that they have actually in their control. So there's definitely different hoops that are beyond the purely technical for why they couldn't necessarily do this. What we're trying to do is establish a more, I would say, a looser coupling with a lot of industry partners, where we actually run problems and create, as I said, these kind of virtual experiments, virtual case, problems of interest, so that that they can then take back and use as they see fit to improve their design processes. Now, having said that, there have been cases where we've had direct industry tie-in. So we did that a lot in Castle with Westinghouse, for example, and EPRI, where we were able to get specific plant and operational data as they were starting up, for example, Watts Bar 2 here at TVA. And we were able to do direct models of Watts Bar 2. And we worked through all the details of putting these on proprietary partition of Titan, ran the simulation, and were able to compare to their startup calculations, and then ultimately compare to the actual startup itself. Mm-hmm. And so that can happen, but there's not a what I would call as smooth as you'd like to see mechanism for doing that on a regular basis.
Do you think it's important, or is that sort of lower on the tier?
No, I actually think, from a nuclear industry standpoint, I actually think it would be very important. I would like, obviously we'd like to see everything we do get used, and some industries have embraced higher performance computing more than others. A good example of that is the aerospace industry. The aerospace industry has gone much more over the decades into using the most powerful computers they can or get their hands on to do their design calculations. And it's a similar workflow as in nuclear. We used to have hundreds of wind tunnels around the country, and now there's only a handful that can at least do big wind experiments. And so what they've done is they found that they can save a lot of money by operating fewer wind tunnels and iterating with computation to develop their new airframe designs. And in the end, that becomes a win. So, but they've made a very strong institutional push over a long period of time to invest in high performance computing that hasn't been as robustly done on the nuclear side outside of the national labs to date. And so, hopefully kind of like these kind of informal partnerships between industry and the labs is going to push the entire industry in that direction a little bit more.
Yeah, I guess maybe the start of that would be to get enough designs out that aren't proprietary that you guys can start to work together more, or at least focusing on the ones that we already have. And
that's what we've been doing. Yeah, we've been using kind of that have what I would call all the salient features of the proprietary designs, but have been certified for open use.
Right. And so you get to see a lot of the different, I would say, technologies up and coming in the nuclear industry, from the supercomputing to the actual physical technologies. What do you see as the future of nuclear? Do you see it being these advanced technologies, or do you see us fine-tuning ones we already have using the supercomputing tools?
Well, okay, so from the future of nuclear, I see a continued emphasis on smaller, more portable reactor designs. So for example, I think, the kind of the concept of SMRs originally was the idea that you'd have one site that did, the design fabrication, and then the plant itself was some sense divorced from the core. So you're kind of, you could, in some ways you think of a nuclear plant as no different than any other power plant. It's just the heat source that's fundamentally different, right? And so if you look at an SMR, all the primary heat exchanger is integrated into the core module itself. And the idea is you can almost think of these as like, a much bigger form of a battery, right? So, these things are prefabbed at one site. So you worry about certifying one site to handle nuclear material, to handle all the safety considerations of building and developing and managing the capital costs of a core construction. And you bring those to a place to an existing plant, you drop them in, you run power, and then, you pull them out. And so having this kind of prefab approach to nuclear, I think, is probably the approach that works best. If you look at where we are right now, the thing that seems to stymie new nuclear construction is capital costs on site, right? So this seems to be a reasonable approach to getting around that otherwise, difficult problem to solve. Is how to manage the exploding capital costs on site for new nuclear construction. And then obviously going to smaller cores that are, more agile, that you can bring power in some sense where needed, as opposed to having these big monolithic, 700 megawatt plants, which are just bulky and unyieldy, again, from a capital cost standpoint, I think is where the future goes. And so obviously, if you're looking at new reactor designs, the more, small reactor designs, the more modeling and simulation you can use to speed and get confidence in the operating parameters and operating constraints of those designs, the better off we're going to be. And again, this all comes down to ultimately optimizing, if you're talking about new construction, optimizing capital costs, right? So if you can kind of focus on, one site that's going to build, certify, design these kind of small cores, and then distribute them to plants that can accept those, I think that's ultimately where nuclear probably needs to be.
Yeah, well, I look forward to seeing where it ends up, especially thanks to your work.
Well, we hope.
Thank you so much, Tom.
Oh, yeah, you bet. Thank you very much.